Hello and welcome to today's Authority Partners webinar about distributed events and diving into challenges and best practices. I'm Richard Šeherac, Solution Architect at Authority Partners. Throughout my career, I had opportunity to work on several large enterprise systems, and all of them utilize some form of distributed events and event-driven architecture to achieve specific business needs. And in my experience, I noticed that design and implementation in these distributed events often gets oversimplified. This then leads to different kinds of challenges and ultimately to unmaintainable solutions, right? So this was the ultimate motivation behind organizing today's webinar, so we could holistically explore this topic. I'd like to welcome my dear colleague and renowned expert in software design, Steve Smith, to join me. Steve, it's always a pleasure working with you and diving into deep discussions with many permutations. I'll pass it over to you to introduce yourself.
Thanks, Riyad. Hey, everybody. I'm Steve Smith. You may know me online as R. Dallas because, at least in the United States, Steve Smith is an incredibly common name to have. And like Riyad, I've got a couple decades of experience as an architect and developer building systems for enterprises. And in many cases, they're distributed systems. They might use microservices, and they almost always have some element of asynchronous messaging and event-driven nature to them. So I agree with Rihad that in many cases, the original approach to these designs is overly simplified and fails to account for some of the problems that you can run into. And so today we're going to talk about, what are some of those pitfalls and how can you avoid them?
Thank you, Steve. Once again, welcome everyone. So on this webinar, we'll quickly go through a short introduction of distributed event systems, and then we will focus on several concepts that often get overlooked or misinterpreted. Our goal is to share our knowledge and experience with you, offering holistic view into topic. So it should help you build robust and scalable and maintainable systems in the future. So let's get started. Share here. So before we get into this topic, let's quickly go through the format of today's webinar. The bulk of the time today, Steve and I will be going through selected topics with some examples and discussions. At the end, we will open the floor for your questions. To submit a question, you can use that questions options at the bottom of your screens, and we will try to answer as many of your questions as time allows at the end. But first, let's say a word about Authority Partners here. Change slide, come on, thank you. So Authority Partners exist for over 2 decades, delivering custom solutions to the clients. Solutions are custom tailored for increasing clients' productivity and for assisting with their business transformations. Here's a view of our service offerings. And I must say, it's very interesting that today's topic fits into all of these categories, right? Which is some form of proof about versatility, I would say, of these distributed events. So Steve, would you help us understand distributed event systems and possibly difference between distributed event systems and message-driven architecture?
Sure thing. So let's start by defining distributed events. And of course, we'll just go to Wikipedia as the source of truth for this. Essentially, distributed events are a way for different systems or different parts of a system to communicate with one another and let them know about something that has changed or something of interest. So each one of these events that are in this distributed system are a thing that happened in the past. Usually this is going to be a state change to some type of an entity. Sometimes it'll just be a thing of interest that occurred and you want to let other parts of the system know about it. In any case, the purpose of these events is to allow for synchronization between these different systems in an asynchronous way that doesn't allow for or require any direct synchronous dependency. So for example, another way that you could achieve this would be to have, system A, when something happens, system B needs to know about it. It could call an API endpoint on system B, but that would require a synchronous real-time connection to do that. using distributed events, you don't need that approach. The other part of this that you want to realize is that these distributed events usually sit on top of event-driven architecture, and so event-driven architecture is a key part of this discussion. So when we talk about event-driven architecture, events is obviously like the most important thing. Like it's right there as part of the name. And so it is true that a lot of the time these things we're talking about are in fact events, where an event is something of interest that happened, it's in the past, and we're just going to broadcast it and let other parts of the system know. But it also has to do with other types of messages. And the two types of messages most commonly used are commands, which are the most common, and then also occasionally queries. So queries you often will use with a synchronous call, but in some cases it makes sense to use an asynchronous query and send a message with that query and then get back a response. And so if you think about these three types of messages, you have events, commands, and queries. Commands and queries you may be familiar with from API design, where we'll often use command query responsibility segregation, or CQRS, to group those into separate sets of logic. When you're looking at them as messages, a command is a point-to-point thing where you issue a command and it should be processed by exactly one consumer on the other end. There might be many consumers listening to the same queue, but only one of them will perform the operation if things are architected correctly. When you look at queries, it's similar. Only one thing is going to respond to that asynchronous query. And when it does, it's going to send back a response on some other asynchronous channel so that you'll get back that result. And so the difference between queries and commands, of course, is that commands are pretty much fire and forget. Queries have some type of a response coming back on another channel. And then with events, it's a different model because you're publishing an event and you don't know if anyone is listening. You don't necessarily care if there's anyone listening. There might be 0, 1, or many different things listening for and reacting to that event. So event-driven architecture, you could also kind of call that message-driven architecture, where most of the communication for the async collaboration between these systems is done through these sorts of messages.
That's what I wanted to add. For our presentation today, we are not distinguishing these, right? So we're just talking about general messages. We are not considering actually their purpose, because they're all handled in the same way, basically, eventually. So let's quickly see what are typical usage scenarios for distributed events. So we're starting with microservice architecture, where the main goals are to decouple services and to increase scalability. And without going into details, let's just say that this requires increased level of communication, right, between services, increased number of events and everything. So proceeding with real-time data processing, in this case, we're talking about streaming data and event sourcing. In both cases, focus in mainly on managing large number of events, right? And then my personal best, integration of heterogeneous systems, where we're typically integrating multiple enterprise systems and where we are enabling them to work together cohesively, hopefully, without too many bugs. Or we are synchronizing data between systems, right? And we are also implementing some additional logic while we are synchronizing data. As I already mentioned in the introduction, this scenario is used on huge number of cases, and almost every project that I worked on had some kind of event-based integration with external system. Let's continue. So in some case, we might need additional responsiveness on user interface. So we are utilizing events for real-time updates and for publishing accurate notifications to end users. And lastly, for automation and orchestration of business processes, right, where events are essential for automating these business workflows, like order processing in e-commerce, and for coordinating complex processes between multiple services. So Steve, tell me, what's your personal best in this?
I think, yeah, probably the place where I use events the most is in microservice architectures, either fully microservice, where everything is a microservice, or something that's more of a modular monolith, which is generally my preference. And then you have some microservices where it makes sense to spin those off. I've also used them quite a bit with responsive user interfaces using SignalR or WebSockets and being able to respond back to the browser and have a toast notification or something pop up to say, something took place successfully. That's very common these days, especially with single page applications and push notifications for mobile apps. So distributed events work great for that scenario too, I've found.
Yeah, I would also vote for the left side of this slide. This is mostly where I've used events. So real quickly, what are the key benefits and challenges related to distributed events? Some benefits we already mentioned: loose coupling, scalability, real-time processing. And let's also mention fault tolerance, where we use events for increasing system resilience, right? In this case, we have events saved and available to be retried and potentially replayed in case of need, right? So some of temporary issues that happen can be resolved this way. Talking about challenges, obviously there's added complexity in design because nothing comes in free for free. There's also increased need for monitoring and debugging, which is crucial for maintaining system reliability. And there are also security considerations, right? Since processing is distributed across multiple nodes, so we might need to ensure proper authentication, authorization, encryption mechanisms. Going back to monitoring and debugging, it's sometimes the only way to understand if something stopped working, if some events are not flowing as they should, so really important because things are happening, aside from everybody's eyes. So that's it from the short introduction. Now let's quickly see flow to today's webinar. So there were many interesting topics about distributed events, so we decided to split discussion in 2 sessions. In first session, which is today, we will talk about different design concepts and transport layer. And in the second session, we will cover approach for handling and monitoring events, and also add some notes on security and compliance. So before we dive into this, just a quick reminder to send your questions and comments. We'd like to hear your thoughts on these topics here. This is the point where we overwhelm you with huge list of different concepts and practices. The list is long, but we'll try to focus on key things related to distributed events. So one area is general understanding of design, design related to distributed systems. And we will also go see, what was the approach to defining event contracts. Just mentioning the need for investing into documentation and training for optimizing learning curve, and securing strong governance within the company. We will not talk much about this. So Steve, let's dive into details.
All right. So one of the first things that I like to talk about and make sure people understand when it comes to distributed systems in general and event-driven architecture in particular is that you run quickly into the fallacies of distributed computing, which I know many of the listeners you are probably familiar with. These are a set of assertions made by Peter Deutsch and others at Sun Microsystems decades ago. And the issue here is that if you have been used to building systems that run in a single process or thread on one machine, and then it's, you just decide that, the endpoint of one method is now across the network as an API call, or even worse, an async message connection, right? You're going to have very different behavior. And so if you assume that because you're used to writing things where this method calls this other method, and of course it's instantaneous and, it always works and it's never down, right? Short of the whole process crashing, right? Then you're going to run into some problems. So the first rule of distributed systems is don't distribute your system unless you have a really good reason to, because of all these problems. But you want to make sure that you don't just assume that the network will always be there, that it's reliable, that you can count on it. You shouldn't assume that everything is going to be instantaneous. The time between when you call one method and it starts processing that method is nanoseconds, right? But that's not going to be the case over a network hop. And you won't necessarily even have infinite bandwidth. right? You can be as chatty as you want with calling methods locally, and it generally won't have a massive performance degradation unless it's doing lots of memory operations or something like that. But you can very quickly run into bandwidth limitations over the network. So you need to be careful with how much data you send, and also how chatty you are, how many operations, messages, et cetera, that you make. You also can't count on the network being secure. Generally, we're not worried about securing a call from one method to another method in our own application, right? But with a network transport involved, you often are going to need to deal with authorization, authentication, encryption, all those things, because that message is going over a network and you can't be sure that nobody's listening. And given that the network exists outside of your application, you can't necessarily even guarantee that the topology won't change while your application is running. So in our in-process application, we don't expect that this method that we're calling is suddenly going to be somewhere else, and we have to figure out where it is and have some type of way to discover it. But on the network, that service that you're calling, or that endpoint that's listening for your message, it could move, or maybe it didn't even exist when you wrote your app, and somebody has just stood up a new application somewhere on the network, and it needs to listen to your messages, right? Those are all things that can happen after you've deployed your app that you would never consider in a typical, non-distributed application. You also have to remember that in enterprises, there's not just necessarily one administrator. So you may have to work with other teams or other organizations in order to set up and monitor and manage all these network configuration challenges, and that can often result in a lot more communication overhead. The transport cost in literal dollars or in performance or both is another thing that you don't generally consider locally inside of an in-process call. But again, with the network, especially if you're using cloud providers, right, you can run up your cloud hosting charges very quickly if you don't understand how you're being charged for use of things like Azure Service Bus or SQS or whatever tools you might be using. And finally, the network may not even be homogeneous. It may use different transports, different technologies in different places. So you may assume that the way you're going to communicate with everything is through, let's say, HTTP, but then some other parts of the system may use gRPC only. And you have to have some way to deal with that in your application. Not a thing you have to worry about with typical method calls. So all of these things become issues and learning curves for new teams when they're first getting into building distributed systems and event-driven architecture.
Yeah, exactly. I mean, these are called fallacies, right? Misconceptions, or people forget to think about these things.
That's right.
I would personally go back to this latency zero and bandwidth is infinite. How many times we had that scenario? Everything works on my local machine, but once I deploy it in the environment, we experience various performance issues, unexpected delays, race conditions, concurrency issues,
right?
Or even even worse, payment pricing issues and everything.
Yeah, but I don't understand. It worked so fast when I was the only user and it was on my machine, and everything was local. But as soon as I deployed it out to the cloud, everything went really slow.
Everything
happens
works
all the time.
I never had this, race condition locally. Okay.
All right. So another feature of distributed systems generally, and event-driven architectures in particular, is the use of this pattern called eventual consistency. And eventual consistency means that the system may be inconsistent for periods of time or for different parts of the system as operations propagate from one part of the system to another. And so as a really simple example, imagine that you have two systems involved. You have system A on the left and system B on the right. And in the initial state, they have the same data in both places for something that they need to coordinate on. All right. But then a user makes a change and updates system A, right? And so as soon as that happens, system A has now got a new version of whatever the data might be, and system B still has the old version. And so now the system overall is inconsistent because they don't have the same information. And a way that event-driven architectures will deal with this is to issue an event. And so A will issue a whatever updated event and put that on a queue. And at this point, they're still inconsistent, right? Because there's no guarantee that system B is going to get that event anytime soon. It could sit there for a while. But eventually, system B should receive that event, update its local version of that data, and now, once again, they're consistent. So eventual consistency is also pretty normal in the real world. For instance, if I go to the coffee shop and I order a coffee, they may start making the coffee before I even pay, which means if I change my mind and get out of there, now they're kind of left in the lurch where they've wasted some resources. And then I do pay, and I don't have my coffee yet. So now I'm out some money, and I haven't received anything for it. But eventually, I will go to the end of the queue and get my drink, and now everything is consistent, right? I've paid and I've received my product. So we deal with this type of eventual consistency process in the real world all the time.
And I must say, everything sounds very simple and natural, but I'll ask you again after looking
it's always
deeper.
just that easy.
Yeah, I'll ask you after looking into transactions management. So transactions. What are transactions? They are crucial for maintaining data integrity, especially in concurrent operations and system failures. I mean, we all know them. And we usually think about transactions like in this simplified example, right? We would start transaction, we would do some operations. If everything goes well, great, we commit. If something fails, we roll back like nothing ever happened, right? And these are basically called async transactions, right? And async transactions, refer to set of properties required to ensure reliability of transactions. So let's quickly just remind ourselves what this means. So A is atomicity, where we usually say all or nothing, like in this example right here. It's based on commit and rollback. Then we have consistency, which implies to validation and data integrity. At any point, data will not be inconsistent, so it has to go through all the validation process. Isolation, which considers concurrency control, often based on locks, so sometimes not very good, right, to lock half of database. And durability, which is basically guaranteed persistence and recovery. So at any if at any moment during the transaction something happens, power outage, anything, nothing will get lost, right? We will be either in one consistent state or in another consistent state. So we will not enter inconsistent state by any way. So these mentioned async transactions are not really suitable in distributed environments, especially when single transaction spans across multiple processes and databases, or even networks, as we mentioned. So in distributed processing, services could even be implemented using some totally different technology stack. That's not to be ignored. And we might also experience various network failures, process crashes. So for maintaining changes in event-driven architecture, see, I scratched transactions, I'm talking about changes. We utilize patterns like eventual consistency, which was discussed, idempotency or idempotent operations, meaning that we can execute same event or same routine multiple times without duplication, or any other negative side effects. We will cover this more in the next session. And sagas are, saga pattern is typical approach to managing these changes in distributed systems. We will discuss this in a bit more details. But first, let's mention also some alternative approaches closer to async transactions, where we are relying on common protocols and infrastructures, common like shared between all participants, right? So we can have distributed transactions, we can have transactional messaging, we can have transactional databases. All of these methods require some kind of centralized component for coordinating the individual transactions across all services, and practically it joins them all into one large transaction, right? Here's the example that you might have seen somewhere. This is an example of three-phase commit protocol, where we can see complex communication between coordinator service and participant services. So, different components exist there. So, Steve, any thoughts? Can we make these async transactions kind of working, in the distributed events?
I mean, people have tried this, and I'm sure some folks are still running systems that use distributed transaction coordinators. I have nothing but bad experience and memory from using Microsoft Transaction Server back in the Com Plus days. The performance was generally extremely poor, and trying to have all of these systems coordinate in real time in these transactions will make it so that if any of them have any type of hiccup or delay, it can cause significant issues, and they all have to be able to coordinate like in real time. So you don't get the benefit of using this async message bus, message passing type of pattern, right? You have to have all those systems in live communication essentially with one another in order for this to work. And that kind of violates some of the principles of microservice architecture, where you want those services to be independent of one another.
Yeah. My experience is similar, where we tried implementing these in a couple of occasions, but it was overhead. So let's go back to your example with eventual consistency. So what happens if system B fails to update its state? Following previous analogy with ordering coffee at cafe, I might never receive my coffee, right? I might stay inconsistent here.
Right. And that happens in the real world too, right? I mean, what if system B crashes at that moment, and when it comes back up, maybe they redeploy the system, and it doesn't understand how to parse that event anymore for whatever reason, right? They updated the version incorrectly, right? So now it never gets it, and it blows up, and that event's lost. It could be that in the coffee shop, somebody pulls the fire alarm and everybody runs outside, and I already paid and I was waiting in line, but the staff and I are all sitting in the parking lot, and I'm not getting my coffee. So in the real world, they might fix that by like, hey, after we all go back inside, I get my coffee, or the manager gives me a gift card and apologizes. In our system, we could have some administrator or developer that sees that event failed. Most of these technologies we will use will have something like a dead letter queue where failed events go if they can't be processed, and someone is monitoring that, hopefully. And so they could take that message and try to replay it, and system B might be able to process it now, or maybe you have to make an update to system B so it can process it, or maybe you have to change the event itself and then replay it so that it can be processed. But there are ways that we can try and make it work eventually. What's worked for you?
I mean, the takeaway from this for me is that eventual consistency is great, right? We're talking about it, very simple, very simple concept, but on its own, it doesn't really solve the issue. Talking about transactions. So if something failed, eventual consistency will not help us without some additional involvement, for retries, for replays, for I don't know. So that's basically where we see that we need something a bit stronger, right? And that's basically where we have the saga pattern here, And since we have a few definitions here, I will be reading from slides here. So what is saga? Saga is sequence of steps or transactions that are executed in distributed systems to achieve larger business process. This process often even spans across multiple services, as we discussed. Each step in the saga is practically local transaction piece of picture that makes all the needed updates and publishes necessary events to trigger the next step. That's the key here. And the last thing, if any step fails, saga executes compensating transactions. But it's not actually saga, right? It's all individual step need to be compensated back in order to revert the complete change, basically.
Right.
So that's I would say concept of sagas here, right? So bold words are kind of important, right? Sequence of steps. Every step is local transaction on its own, and then every step needs to be compensated in case of some failure. So there's no one AC transaction that cancels everything at once.
And you can kind of do all this on your own, but there's also libraries like Service Bus, for example, that have built-in support for sagas. So it makes it a little bit easier for you to build it into your systems.
But you still have to define all the logic, right? And when doing these changes, you must pay attention to do them in such way so you can revert them. If you want them to be revertible, kind of, right? So obviously it's not general concept. It depends on the usage and depends on planning. But it's worth knowing what the basic concept is, right? So we can at least proceed in this direction and plan our design. Couple of benefits and drawbacks related to Saga. Benefit scalability, because each step is managed independently. That's important. Resilience, because Saga can recover from wide number of failures by executing these compensating transactions, and this compensation is not time sensitive. Did we mention that it can also span across multiple systems and everything? No, here it is. Flexibility, right? That we are spanning, we can handle these how to say, compensation of these complex business processes right across multiple services, not limited to architecture, to location, to location, network, anything. So that's highly flexible. Comparing to that ACID approach, where all of them are tied up by that central, how was it called, coordinator, right? So they need to have way to cooperate. Here, everything is loosely coupled based on events. Drawbacks, complexity, obviously compensating transactions are complex as we discussed here. And it's possible to have consistency delays. I mentioned this in resilience, that it's good that it's not time sensitive. It takes what it takes, but sometimes it's not supposed to take as long as it takes, right? So,
and some things are harder to roll back. Like if you have a process and somewhere in that process you want to send an email to your customer, like looking at your sequence on the slide, if you do that in service 1, send the user an email that they've placed their order, and then service 3 fails, like on the right-hand part of the slide, how do you roll back that email send? Like that's hard. And one easy solution is, well, don't do that first, right? Like
exactly.
Do that email at the end.
Don't go in that direction. But obviously it's important mentioning. It's not like let's just order these steps in any way that we want. We have to think what's the best order for our steps, and we should probably have how to say, kind of partial sagas, in our larger process. So if we need to revert, we don't revert 20 steps. We revert 3 last steps or something like that. So
sure.
Yeah, but concept is concept, right? What do we have here? 2 approaches for managing sagas. Anyone wants to guess these approaches?
Yeah. Our audience probably knows.
Choreography. Choreography, already kind of discussed through this example. Each service involved in Saga listens for events and performs its own step independently. And in case of any failure, each service is responsible for executing compensation logic. We see these individual steps. And the other one, obviously orchestration, where there is a central orchestrator that coordinates execution of each step in the Saga. And also, in case of failure, orchestrator is responsible for coordinating execution of compensation logic, right? It's not visible in this diagram, but we can also have parallel operations which complicate things. But I would stop here for now. Maybe a question for Steve. What's your personal preference between choreography and orchestration? Everlasting question, I would say.
Yeah. I think that having an orchestrator for sagas makes it much easier, at least in the early stages of an application or for simple processes, to see all the steps that are going on, especially if it starts out relatively simple and you know it's going to get more complicated. Because if you do everything with choreography, then you have to rely on documentation to understand the whole process. There's nothing in the system that lets you see A, then B, then C, then D, and that's the saga. It's just, this event happened successfully or this event didn't happen successfully, and then magic happens, right? And other things are supposed to react to that. And if they do, that's great. And if they don't, well, you can lose some hair trying to figure out why. So I know that the orchestrator is a single point of failure, but the fact that it lets me see
So
what's going on in one place,
they say it's single point of failure, right? It's not necessarily single point of failure. I want to say everything in this eventing is basically single point of failure. If any of events in choreography or in orchestration misses, everything stops simply.
That's true. That's true.
So no, I don't really buy that. It's a single point of failure. But yes, it could be a bottleneck, possibly even for development, right?
Sure.
Sorry, I stepped into your word. I couldn't resist. But
tell me why I'm wrong.
Yeah. So I was more into orchestration, to be honest. And when I'm talking to some of my supervisors, I will always say I'm for orchestration. Oops. But but after implementing this orchestrator, I see that, as I said, it's potentially a bottleneck. It's the one that manages state, right? It's the one that controls all of these individual services. It needs to understand language of all of these services. It needs to have lots of message conversions to extract data that's needed to each of these steps, right? So events, kind of, it gets overwhelmed with parsing these events and copying data around. I kind of didn't like that. And I have to mention the additional number of events. We see the number of arrows here. So these black arrows on the orchestrator side, they're two-sided arrows. So their duplicate number of messages is required for the orchestration versus the choreography there. And for the choreography, I couldn't really find big issues except what you said, visibility, of entire process, which can easily be solved by documentation, if we are
easily
paying attention.
Yeah.
Not everybody can read workflow definition that we would usually put in the orchestrator as well, right? So,
fair.
I mean, it's everlasting debate. I agree, but let's
the orchestrator is definitely more tightly coupled to the services. Yeah. And okay, so we can always fall back on it depends, right? Use the one that makes the most sense in your system and your architecture.
It definitely depends always.
All right. So regardless of how you're doing that, you're going to be sending these messages, and one of the important characteristics is getting the size of those messages right. In many cases, you might start out with super minimal messages, and they have minimal information in them, like what is the type of the event and what is the ID that event relates to, and that's all, right? And I usually call these data deficient messages. Sometimes they might be sufficient, they might be enough, but as I'll show you in a moment, in many cases they can cause problems. On the other end of things, right, you might have your message include all of the possible data that anyone might ever need, and serialize the entire object graph and half the database into this event to send to whoever might need it. And these are typically called God events or God messages because they probably have more data in them than you might need. And so you really want to strive for events or messages that are not too big and not too small. They're what we call Goldilocks size messages from the fairy tale about Goldilocks and the Three Bears. And you may not know in some cases what is the right size, because you don't know who the consumer is. This is often true for events where you're firing off events and you don't even know who's going to be listening. But in many cases, you do know, right? If you're creating a command and you're the command processor, you can say, this is exactly what I need. Then people can send you that, and it should be exactly what you need. There shouldn't be this challenge of wondering whether or not it should be too big or too small. Okay, so we're mostly going to be talking about events here. So let's talk about the problem with these data deficient messages where you just send out the ID. So this source app says, hey, we created an order for customer 123 and order 456. And 3 consumers get that, and they can't do anything with that. So they have to call back and hit your API and say, tell me about this customer. Tell me about this order. I need to send an email. I need to decrement our inventory. I need to do other stuff, and I need to know the details. And so what happens is you send out one event, and you get hit with, n times however many API calls they need to make of requests back to your API. And you can basically denial of service attack yourself by having this pattern. Whereas if you just included some minimal amount of information, like here's the customer's name and their email, here's the names of the things they bought on their order and the total, like that might not be enough for every consumer, but it doesn't make your message that much bigger, and it will probably be enough for some consumers to act on. And so that's sort of the design challenge you have when you're trying to right size these messages for these events. Now, on the other hand, like I said, you might have the
God messages.
You might attempt to make God messages. Yeah, I'm trying to think of the word I want. Like you might be tempted to just put everything in there, right? And so the problem with God messages that have way too much data in them is that they're much more expensive to produce. Maybe you have to make more database calls to get the data, and then you have to serialize it all, and it uses up more memory. Then you have to propagate it over the system. So it's going to be more expensive in terms of bandwidth. It's probably going to cost you more on your cloud hosting bill. And then they're more expensive to consume. Again, deserializing and memory are both going to be bigger than necessary. And the other thing that you don't necessarily realize when you're designing these systems is you may expect that when you throw that message on the queue and something else picks it up, like almost no time has passed. But in many cases, it's true that the message could be a while before something hits it, right? It might be that it gets replayed. It might be that there's a lot of messages in front of it on the queue, or that the thing that's going to process it was down for maintenance and it comes back up and it's 10 minutes have gone by, right? So the data that's in that message could be stale, and it may be that the consumer really needs to have the latest data. And so if you passing it a whole bunch of extra data at all this extra cost may not be useful, because it ends up that data might be stale anyway. And the bigger the amount of data you send, the more likely the risk is higher that some part of it has changed in the meantime since you sent it, and is therefore out of date. Okay, so let's start to talk about versioning now and backward compatibility.
Yeah. I want to mention, when talking about versioning and backward compatibility, my first thought is usually on REST APIs. So any update in a contract may negatively affect callers, and things are breaking all over the place. So sometimes we would even need to support several versions of the same contract at the same time and everything. So let's quickly look how it looks, in events.
Sure. So yeah, I mean, it's a similar problem. One of the things you need to think about with events is who owns the contract. If it's an API, obviously the API server, owns the contract that it's going to use. But when we're talking about commands and events, it's not quite as clear cut. So generally, when you look at this picture and you can see the product catalog in the center and orange commands coming in from the left and events being fired out on the right, the single end of those fan outs is the product catalog. So it's the consumer of the commands. It's the thing that's going to process those commands. So it owns the commands because it's going to process them. And it's the emitter. It's the source of the events. And so it owns the events because it's the one that's producing them. It's the one that's sending them out. And so it's opposite ends of the communication channel. But the thing that's consistent is that there's only one point on that side, right? Now, when you're talking about versioning in messages, you want to think about it up front, because you want to realize that at some point you might need to make a breaking change to that message format. And what is that going to mean downstream, right? If you've been sending out events for a while and you have apps B1, B2, and B3 all listening, and then you decide to update the version and change it in a breaking way, when they go to deserialize those messages, they might just blow up and not be able to handle them. And so maybe you've got, a NuGet package or something where you update the new schema, and they pick that up eventually, but only after it's been deployed. And even once it has, you have to realize that there might be multiple versions of your messages in the system at any given time, right? You might have a queue with 100 messages on it, and the first 50 were version 1, and then the next 50 are version 2. And so you can't just update the NuGet package for app B1 and have it use the new version, because now it's going to choke on the old version. And so you might have to say that we're going to support, several versions at a time. And it could be also that the catalog maybe figures out a way to send to multiple versions in some way, right? Mark the version on the message. Of course, that's a best practice, but it could even go so far as to have different queues for different versions or topics, and have a topic for version 1 and a topic for version 2. So, Rihad, what do you think? What's worked well for you?
Yeah, I mean, exactly that. I mean, you said it all. Versioning is quite complex, and it's important to be aware of it, right? To plan soon enough. I'll stop on that. We are not the best with time, right?
Yeah, we'll pick it up for the last few. We've only got a few slides left.
So we have covered a few topics related to design of the distributed event systems, but let's also cover several topics related to transport layer, right? So we will briefly talk about reliability and fault tolerance. And we will also discuss specifics of inter-service communication and scalability. It's important mentioning here that all services that participate in communication here need to agree on communication protocol and all payload formats, right? So that's very important. Otherwise, messages won't be able to deserialize, right? So what does it mean using reliable messaging systems? Here are a few suggestions. First thing, using robust messaging system that guarantee delivery, like Azure Service Bus, RabbitMQ, Kafka, clean enough. You can also save events in days. I might, suffer for this, but you can save events into database and then use different methods for taking them out for processing, right? I would usually combine database and messaging system for best performance. We might get back to this. But one thing that I urge you not to do is to use in-memory queues, even when passing events within the same process, because in-memory queues are highly unreliable. Steve, I would mention on this, I would mention example. There was like fully asynchronous part of integrator extracting data asynchronously, looking into statuses and everything, and then passing messages into batches to some service to pass them on, And the service had internal in-memory queue. And,
anytime
you
it
can
crashes,
imagine what happens.
Yep. You'll get some of them done, but some of them maybe not. Yep.
Some of them maybe not. So although everything is highly, asynchronous and everything, there's little in-memory queue inside one of service. Talking about replay capability, I want to say it is very, very beneficial in certain cases, right? So for example, in case of failures due to version changes or in some internal errors, we already discussed this eventual consistency things. So we need to keep track of these failed events always, usually in dead letter queue or in database. Again, database. In case of wrongly processed events, this is very interesting topic. We have time to cover it a bit. This is basically where we integrate again, where we emit some events, and then integrator fails to process these events. Did you have any case of this?
Yeah, and like you say, when you have two systems, maybe there was an acquisition and you're trying to integrate with this new system that was built by other people, and initially you think it's working and you deploy it, but then something you didn't consider causes a bunch of messages to not work, right? You want to be able to replay those same messages or even just a subset of them in order to like test it out, make sure your fix is working, and then once everything's good, then replay the whole batch. And that happens all the time with integration scenarios.
all the time, and these events are physically processed, right? They're completed, they are off the queue, but something failed inside the integrator, that was processing them. So it didn't process them correctly. There was some bug or something. So this is an interesting concept to consider, that it exists, and you might be asked to replace a certain number of messages. And let's also mention here classical use case for replay, although I didn't use it, for initializing materialized views in microservices. So usually, in this case, we would need full history of events. So once we have a new microservice that needs to initialize materialized view, they would prefer to flush all the full history of all events. And in practice, eventing systems often periodically create certain snapshot events and forget all the events. But it's either this or what? Overnight exports, right, of all data into new microservices.
One-off type of initialization. Yeah.
And I would say that there is no uniform solution for this reply capability. Obviously, it depends on scenario that we're talking about. So let's quickly go to the message ordering.
All right, so this is where we want to remind you that if you have any questions, please feel free to post them. We see we've got a few that we'll try and get to. But if you have any, please let us know. And if we don't get to you, we'll follow up with you by email if we can. Okay, so in terms of message ordering, it's sometimes important. And let's talk about a real easy scenario. Let's say that you want to place an order for something, and then right after you place the order, you realize, oh, wait, no, that's not what I wanted. And you push the button to cancel and refund the order. And so there's two messages in play here. They're both commands. There's a command that says, hey, I want to process order number 123. Can you advance the slide for me, Rihad? And then another one that says, hey, I want to refund order 123. And so what happens if these arrive out of order, right? Rihad, if the processor just gets refund order 123 and it gets that one first, what's it going to do?
I mean, obviously, it will fail of some kind, right? It might try to retry, but basically it will fail. I would expect this process order to come afterwards and to charge me for the order. That's my first assumption, I would say.
You as the customer, maybe the user interface says everything was successful, right? Because most user interfaces assume that if they manage to put the command on the queue, that they're good to go. And so the user was told, hey, we got your order, and hey, we canceled your order. But what actually happened on the back end is, hey, we didn't know what to do with this refund thing, and hey, we processed the order. So, they aren't going to get a refund, and their order is going to go through, and they're not going to be happy. And so having some support for message ordering can be important, and there's different ways that we can implement that, and we don't have a lot of time to talk about the details of it. You may have some support for ordered messages in your queuing scenario, but even with that, you may have things go out of order when you do replays or retries or other things. Rihad, do you have anything to share on this before we jump to the next one?
Yeah, I mean, it's spot on, I would say. And I'm laughing because I'm constantly mentioning database. So someone will kill me for this, I promise. But I'm kind of custom guy here. I like these custom solutions, and I see the great level of control in database, right? And
sure.
Messaging systems are good, right? But they're usually there for message delivery part. And I see that they often lack flexibility when we need to order these events or schedule some retries that will happen in some time, not immediately. And that kind of reorders messages significantly. And where are we?
Yeah. And being able to detect messages that are out of order is a challenge. You can't just put a timestamp on it. One thing that you could do is, like on the refund command, it could have a reference to the process order message ID, in which case when you get that and you say, hey, this depended on this other message ID that I don't have, right, then that can be a way for you to detect it and maybe hold on to it for a period of time and wait to see if you get that one that you're expecting.
But will you get the same event or another process will get it? I mean, eventually you have to save it somewhere in the database or in distributed cache or somewhere.
Yes, certainly. All right, let's talk prioritization and then wrap it up with some questions. So sometimes you want to make sure that your messages are processed in in a timely manner, and some messages are more important than others. So you may use a priority queue for that. Maybe your messages for processing orders go to the head of the line, but your messages about just diagnostic stuff, can sit at priority 3. The problem with the simple approach is that those level 3 priority messages may never get done, just like all the things on your product backlog that aren't number 1 priorities that you never seem to get to. It's the same idea. So a solution to that is to have different queues for each priority and assign different numbers of resources to them. Go ahead and flip the slide. And so in that case, you might have several consumers for priority 1 and only 1 consumer for the priority 3 messages. This makes it so that you don't have any of them just languishing and never getting to the front of the line, but you can assign resources more appropriately. Now, if you're in a multi-tenant solution or you have a SaaS product, which is pretty common, you may still have a case where one tenant sends off a ton of priority 1 messages, and that makes it so another tenant has all their messages languishing at the end of the line. So the solution, again, is to just add more queues, right? And so you might have a queue per tenant per priority, and that allows you to do a form of throttling. You can have a service level agreement for each one of your tenants that says you're going to get so many requests per second out of this. And then if they send more than that, instead of giving them some type of a response like you would on your API to say too many requests, 429, all that you would do is let those things pile up in the queue, and you'll process them at the rate that you've agreed to in your SLA. So yeah, show that last bullet, and then that gives us a couple minutes for questions, I think, right? All right. So thank you, everybody.
Yeah, it wraps our presentation for today. So I hope we helped you, having better understanding how to tackle these challenges associated with distributed event systems, leverage their full potential in your projects, at least for parts that we covered on this session, right? Let's take a look on Q&A.
So we have one question here. It says, I believe in distributed systems, the CAP theorem is mandating accepting eventual consistency, which I would say is correct. And the question is, if eventual consistency therefore also mandates event sourcing as your storage architecture, is it mandating that instead of using traditional CRUD storage architecture? I don't think it mandates it. I think you can still use traditional CRUD operations, meaning that you're storing updates in a single row instead of having every single change stored throughout the history like you would do in event sourcing. Event sourcing can certainly be useful, but there's plenty of systems that still use eventual consistency and use a traditional database style update approach. What do you think, Rihad?
Yeah, I would agree with that. I mean, one doesn't exclude the other. Yeah. What else?
Another question here is we got a couple minutes left.
Have time for a couple more.
What is your preferred cloud vendor for microservices, Rihad?
again, orchestration versus choreography. So, I mean, it's for me personally, it's just a question of personal choice mostly, right? Because we are here, especially in this presentation, we are talking about general concepts, right? So, if needed, we can implement this only in database. Sorry, I'm so stunned with database because I started implementing these, event-based systems, event triggers, directly in database and in non-transactional message queues, So we were handling threads. We were handling threads. We were handling transactions, everything. So, I mean, we can write them however we want. So literally just personal choice. I don't know about you. I mean, I'm more the Azure, my Microsoft guy, Azure guy, but I mean.
Yeah, we use both. I'm most of my stuff is in Azure, but that's because I'm a Microsoft MVP and they give me some free credits. Amazon doesn't do that, so. But we have clients that use Amazon and Microsoft, and even one client that uses Google. So like they're out there. All right.
Yeah. Here's one interesting question. Where we mentioned the execution of parallel operations in sagas, and all the diagrams look very linear process. Can we parallelize operations using events? So actually, yes. Both with orchestration and choreography. I think we will discuss this in the next session a bit more. But basically, orchestrator can issue multiple events, trigger multiple services at the same time, then wait for all of their responses before continuing. And in the choreography world, we would have some kind of, I don't know, official word, kind of control points where single event would trigger multiple services to do parallel. And then at one point, control service would just wait for multiple events to finish before continuing and continuing further.
That word you're looking for is it's an orchestrator.
It's not the orchestrator. It's just wait for multiple events. I mean, it's much simpler than orchestrator. Don't go there.
Yeah. And what does it do if they fail? It sends out new events to say, hey, roll back.
It's the responsibility, of everybody to issue rollback event. Yeah. So I think we're out of time. This concludes our Q&A session. Maybe we could have covered more questions, but okay. So thank you all who participated in this event. You are the reason why we are doing this. And special thanks to Steve Smith for sharing expertise and on distributed event systems. Thank you, Steve.
Yeah, thanks everybody.
For those who wish to revisit sessions or share it with colleagues, recording will be available and shared with you in upcoming days. If you'd like to get in touch with us and learn more about this topic or how we can help you on your next project as Authority Partners, you can send us email on hello@authoritypartners.com or visit our website and use our Get in Touch form. And once again, thank you for joining today. We look forward to seeing you at our next event. Big wave.
Thanks, everybody.